Welcome back to Allen High School and AP Chemistry. We are currently working on electron configurations and working through our electron configurations. Now we had just done one for antimony, and I know this says selenium, but we're going to change that to tungsten because actually I've already done selenium for you. So we're going to do tungsten because that's going to get us through the F block. So let's take a look at where tungsten is. If you look at your periodic table and count in 4, it's going to be right here. So that's where we're shooting for. Now, this is where we have to take our detour. We can do it either here or here, but I like to do it right here because by and large, you're not going to be asked to do the ones that are right at the beginning in here. You'll be asked to just go through the F block if you are asked that at all. So let's start with tungsten. We need to start with 1s2. You start way back at the beginning. I'll show you a shorter way to do this soon. Then we go left to right, 2s2, cross the ravine, 2p6. We're nowhere near there yet. Wrap back around left to right, 3s2. Cross the ravine and hit 3p6. Wrap around, 4s2. Now remember, when you get to the D block, you got to dip down 1 for N. So it's 3d10 instead of 4d10. And then we pick back up to 4p6, come back around, and it's 5s2. Dip down for your Ds, 4d10, 5p6. And we're here. We filled up to here, and we need to come back here. Now, this is where we're going to have to take a little detour down to our F block. So we have 6s2. Now, instead of crossing into our D block, because really these belong in the periodic table, and an expanded periodic table, it would split right here, and these 2 rows would be sit right into here. So we're going to come down here, and this is the 6th period, so it's the 4F block. And if we go all the way through that, there's 14 electrons. Then we can pick up right where we were before. And we're at the D block, so we have 5D, and we're not going to go all the way through, so we have to count 1, 2, 3, 4. So this would be 5D4. Now, this is very, very long to write. And you notice that it gets pretty repetitive. These elements have very similar electron configurations. So what we do, there is a noble gas configuration that goes to the previous noble gas, not the nearest, the previous noble gas. And for tungsten, it's going to be right here at the end of 5p6. And that happens to be xenon. So what we would do is represent that with a bracket in the xenon. And that tells us that it's the electron configuration of xenon plus 6s2, 4f14, 5d4. So that's called the noble gas configuration, and you'll see it used quite a bit off and on. You can't really give it unless it specifies. Because typically, if you're asked to give an electron configuration, the questioner is asking to see if you know what that filling order is. Again, remember, we're doing ground state. Now, on the other hand, it's not uncommon to see this type in a multiple choice question, because then it's a less of an issue to see if you know that filling order. So that would be tungsten. Let's answer these other ones. Which element has the following electron configuration? Again, those superscripts tell us how many electrons are present. So since we know that it's an element and not an ion, we can add those up, and we could come up with our total number of electrons and find out which neutral element has that many electrons. Or if you know your periodic table well, and this is exactly why I like to use the periodic table and not that tree method that many books show you, is we can zero in at the end of our walk. So if we end in 5s2, since it's the S block, I know I'm somewhere in here. ending somewhere between those two columns or families. Now, since it's S, I also know that N is equal to my period number. So if N is equal to 5, it must mean I'm in the 5th period. So I'd go, this periodic table is labeled, but I'd have to count in a normal periodic table, 1, 2, 3, 4, 5, and I went in 2, so 5s2 would represent this element here, and if you look on your periodic table, that happens to be strontium. So that's how you can find that. Now, it says to assign quantum numbers to the last electron in B. So you can't see that here, but that's what it is in your notes. So in other words, I want to assign quantum numbers to this electron. So let's kind of clean that up a little bit so we can see what we're doing. I want to assign quantum numbers to this electron. Now, since it's 5s, I know n is equal to 5. Since it's s, I know L is equal to 0, which means m sub L has to equal 0. Now, this represented the first electron that went in. This was the first electron that went in. Therefore, this is the second electron in that sublevel and orbital. So that means m sub s is equal to minus 1/2. Because it's the second one in. And by convention, the first one is plus and the second one's minus. Okay, so that's how you assign quantum numbers to that last electron that we were putting in there. Now, the next thing it does is ask you to write the electron configuration for chromium. Now, to get the electron configuration for chromium, you want to find chromium on the periodic table, and it's right here. And I would very much like you to pause the video before we show this, because I want to go on and show you some unusual aspects of the periodic table. So pause it. You don't have to, but honestly, you'll get the best learning out of this if you do. So I'm going to go ahead and start. You always start at the beginning. I have 1s2, then come back here. You always wrap left to right, just like you read. 2s2, cross the ravine. I'm not there yet. 2p6, come back to the beginning. 3s2, cross the ravine. 3p6. Then I'd come back here. I'd have 4s2. And now, remember, we bumped down for the d, so it'd be 3d instead of 4d. Count in 1, 2, 3, 4. So you'd put 3d4. Now that's what you would predict for the electron configuration for chromium. Now, in reality, chromium does not behave like chromium should behave. And that's where we get a whole series. We're only going to learn 2 groups. One group doesn't completely do this, but most of it does, that we call irregular electron configurations. It might be similar names to that, but the key is they're electron configurations that are an anomaly. An anomaly really kind of goes against the rule, doesn't follow what the others are doing. So the 2 that we're going to look at are chromium and copper. And we predicted for chromium that it would be 4s2. Let me do the shorthand notation just for the sake of time. We go to the previous noble gas, which is argon. So we'd predict that it would be argon, 4s2, 3d4. Now, for copper, it's very similar, but it's towards the end. Again, we would have the previous noble gas, not the nearest, the previous, keep writing copper there, previous noble gas, which is argon. I do argon, 4s2. This time, if you count into copper, you'd see 3d9. Now, what we want to look at is what it is actually. Now, when studies are done, it is found out that actually chromium does this. You can call it kind of an S-hopping. One of the S's goes to the 3D. So it'd be 4s1, 3d5. Now, to justify it, you'll see some books say that half-filled are more stable. But that's not a justification. That's simply an observation. It doesn't tell us why they're more stable, it just tells us that they're more stable. So that's not enough. That is not a good quality justification. You might start with that sentence, but you need to, finish it with a because. So let's draw this out. We had 4s and we had 3d. Now remember that the 3d are closer to the nucleus. These are lower in energy, so that's the advantage of the 4s. Now, what we predicted would have looked something like this, but these are so close in energy here that what this electron can do as it seeks to maximize getting closer to the nucleus while minimizing electron repulsion, if this electron hops up to here, do you notice that it will have less electron-electron repulsion because it went from being paired to all being unpaired. So chromium, instead of having 4 unpaired electrons, would actually end up with 6 unpaired electrons. And unpaired electrons experience a little less repulsion than paired electrons. Got to do copper fast or we're going to run out of time on our video. What we see with argon is with copper is a similar thing. It's a little harder to justify. You don't get quite the electron-electron repulsion issue that you have, but what we end up getting, so this is the 4s, 1, 2, 3, 4, 5. So what we end up getting is it went from being a paired to being a paired. Okay, paired here, paired here. So that didn't help, but it did get that electron a little closer to the nucleus with only a tiny little compromise in energy. So those are our irregular configurations. Next, we will be looking at excited states. By the way, you will notice that not only does copper do this, but not surprisingly, the family does this. And not only does chromium do this, but molybdenum does this. Now, tungsten tends not to. It's pretty big, and it's not as observed as much in those. So those are the only ones that you will be responsible for. There's many more anomalies or unusual or irregular configurations. So, but that's what you need to know. We're going to go on to excited state.